What if I told you that an 18-year-old kid from Tennessee, working alone in a garage with nothing but a welder and some scrap steel tubing, invented something so effective that professional racers with $20,000 worth of suspension equipment couldn't believe what they were seeing? We're talking about a setup that cost $55 total. $55 that produced 1.32 60-foot times. The kind of launch that snaps your head back so hard your brain needs a moment to catch up with your body. The kind of numbers that professional drag racers were spending entire racing budgets chasing. And a teenager beat them all with material you could find at a scrap yard. This is legacy motoring, and I spend way too much time thinking about suspension geometry and drag racing history. If you're someone who loves the engineering stories behind motorsport innovations and wants to understand how one simple idea changed drag racing forever, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, here's the thing. Before we get into how this invention worked and why it was so revolutionary, we need to talk about the world it was born into. Because context matters here. A lot. The drag racing scene of the early 1970s was brutal in a specific way that doesn't get talked about enough. It wasn't just competitive. It was financially stratified in a way that felt almost designed to keep regular people out. If you showed up to a serious drag strip with a leaf spring car, you basically had a target on your back. The established racing community had already decided what you were, and what you were was slow. Or at least slower than the guys with the expensive setups. And for a while they were right. Picture it. It's 1975. You're standing at a drag strip somewhere in Tennessee. The air is thick with that particular combination of tire smoke, racing fuel, and summer heat that anyone who's ever spent a Saturday at a track will immediately recognize in their memory. In one lane, there's a guy with a purpose-built race car. Tubular chassis, a 4-link rear suspension that took a professional shop weeks to fabricate, coilovers that cost more individually than most people's monthly rent. This guy has maybe $20,000 invested in his rear suspension setup alone. Just the suspension. Not the engine, not the transmission, not the bodywork. Just the bits that connect the rear axle to the chassis. In the other lane, there's a kid. Beat-up Chevelle. Leaf springs hanging under the back exactly the way they came from the factory. No chrome, no fancy brackets, nothing that screams race car from 20 feet away. But if you look closer, and most people at that track didn't bother looking closer because they'd already written this car off, you'd notice something. There are these parallel bars running from the axle housing forward toward the frame. Simple, clean, almost primitive looking. The kind of thing you might not even notice unless you knew what you were looking for. The Christmas tree counts down. Both cars launch. And something happens that nobody in that crowd expected. The kid Chevelle plants those rear tires into the asphalt like they're magnetized to it and rockets forward with a violence that matches the purpose-built race car exactly. The guy with the expensive 4-link setup is in disbelief. He just got his doors blown off by a teenager with welded steel tubes that probably took an afternoon to build. And here's what makes this story genuinely extraordinary. It wasn't a fluke. It happened run after run after run. The consistency was as shocking as the speed. This is the story of how ladder bars revolutionized drag racing and became the greatest suspension equalizer in the history of the sport. But more than that, it's a story about what happens when someone refuses to accept the conventional wisdom that expensive is the only path to fast. It's about a teenager's intuitive understanding of physics outsmarting millions of dollars in professional racing development. And to really understand why it was so revolutionary, why it shocked an entire sport and permanently changed it, you have to understand what racers were dealing with before this invention showed up. Here's what most people don't realize about leaf spring suspension under hard acceleration. The problem isn't actually the springs themselves. Springs are doing exactly what springs are supposed to do. The problem is torque. When you hammer the throttle on a rear-wheel drive car, the pinion gear wants to climb the ring gear. That rotational force, that twisting energy has to go somewhere. And in a leaf spring car, it goes straight into the springs themselves. Under hard acceleration, those springs want to wrap up into an S shape. The more power you're making, the more violent that wrap-up becomes. And this is where everything falls apart. Because wrapped springs store energy unpredictably and release it unpredictably. Sometimes that stored energy releases into forward motion. Sometimes it turns into wheel hop. Sometimes it just spins the tires. You genuinely couldn't predict which one you'd get on any given run. Now, you might be thinking, okay, so what were the solutions people were using? And here's where it gets really interesting because there were 3 options available, and they all had serious problems. Option 1 was slapper bars. Crude devices that bolted to the front spring eye and extended back under the axle. The theory was that when the axle rotated under acceleration, the slapper bar would hit a rubber snubber and plant the tires. In practice, they worked with all the consistency of a coin flip. You'd get a great launch one run and then spin the tires on the next run with identical conditions. Bracket racing, which is all about repeatable elapsed times, was essentially ruined by this inconsistency. Option 2 was bolt-on traction bars. These clamped to the leaf spring and were supposed to prevent spring wrap-up by making the spring rigid. The problem with this approach is fundamental and kind of obvious once you think about it. If you make your leaf spring rigid, it stops being a suspension. Every imperfection in the track surface, every tiny bump, every expansion joint, transmitted directly through the car. Your traction was marginally better in perfect conditions, but the car became nearly undrivable in anything less than perfect conditions. And they'd eventually crack your springs, which is a particularly cruel way to end a racing weekend. Option 3 was the nuclear option. You tore out the entire rear suspension and installed a proper 4-link setup. Cut off the spring perches. Weld in new mounting brackets. Fabricate or buy a complete 4-link kit. Install coilovers. Re-engineer the entire rear geometry of your car from scratch. You were looking at thousands of dollars in parts alone before you even started talking about labor. And once you committed to this path, your street car wasn't really a street car anymore. Those 4-link setups were brilliant for racing, but the ride quality on the street was absolutely savage. Every expansion joint felt like a personal attack. So the established wisdom was clear. You had exactly 3 options for dealing with leaf spring traction problems, and none of them were good if you were a regular person trying to race on a real-world budget. The professional racers and the chassis shops had everyone convinced that good traction required complex geometry, expensive components, and essentially surrendering your car to full race duty. There was no middle ground, they said. You either dealt with inconsistent launches, destroyed your suspension chasing a solution that didn't work, or you opened your wallet wide and converted to a full race setup. And then a teenager in Tennessee looked at his leaf spring Chevelle and thought, there has to be a better way. What's remarkable about this part of the story is the specific type of racing this kid was involved in. Bracket racing. And bracket racing context is crucial here, because bracket racing isn't about being the fastest car in the room. It's about being the most consistent car in the room. In bracket racing, you pre-dial your predicted elapsed time before the run. You're not trying to beat your opponent on raw speed. You're trying to run as close to your predicted time as possible, while your opponent tries to do the same. Inconsistent launches weren't just annoying in this format. They were race-ending. Every time your car launched differently than the time before, you were losing. This teenager understood something that the established racing community had somehow managed to overlook, or perhaps understood but hadn't yet figured out how to solve affordably. The physics of the problem pointed directly at a specific solution. The problem was axle rotation. Not spring flex, not suspension compliance, not any of the other variables people were chasing. The specific mechanical problem was the axle housing trying to rotate under acceleration, and the springs being asked to control that rotation while simultaneously supporting the car's weight and providing ride compliance. That was too many jobs for one component. The solution wasn't to make the springs do their job better. It was to give the rotation control job to a different component entirely. Here's the elegance of what he figured out. Instead of trying to prevent spring wrap-up by making the springs rigid, like traction bars did, instead of replacing the springs entirely, like four-links did, he decided to work alongside the springs. Let the springs do what springs are genuinely good at. Support the car's weight, provide vertical compliance, absorb road imperfections. But add a secondary system whose only responsibility was controlling rotation. A system that would allow the suspension to move freely up and down but would immediately and completely prevent the axle housing from rotating. The solution he came up with was two parallel bars, simple steel tubing, running from mounting points on the axle housing forward to mounting points on the frame. Each bar would pivot on both ends using rod ends, which are essentially heavy-duty ball joints. This pivoting action meant the bars could freely accommodate the vertical movement of the suspension. The wheels could go up and down exactly as they needed to. But because the bars were parallel and fixed at both ends, rotation of the axle housing was mechanically impossible. The moment the axle tried to rotate under hard acceleration, those bars transferred that rotational force directly into the chassis, instantly, without any stored energy, without any of the unpredictability of spring wrap-up. The geometry of the mounting points was where the real genius lived. By positioning the front mounting points at a specific height relative to the rear mounting points, you could control something called the instant center of the suspension. Now, the instant center sounds complicated, and in a four-link suspension system it absolutely can be, but here's an analogy that makes it click immediately. Think of a seesaw. The pivot point in the middle is the instant center. Where you put that pivot point determines how the forces on each end of the seesaw behave. Move the pivot point closer to one end and small movements on that end create big movements on the other end. The same principle applies to suspension geometry. The location of the instant center determines how weight transfers during acceleration, and weight transfer determines traction. In a properly configured ladder bar setup, the instant center sits roughly at the height of the car's center of gravity and slightly forward of the rear axle. This specific geometry causes the rear of the car to squat slightly on hard acceleration, pushing weight down onto the rear tires at the exact moment those tires need maximum grip to put power to the ground. It's a mechanical trick that mimics what expensive four-link setups accomplish with multiple adjustable mounting points, except it does it with fixed geometry and no adjustability whatsoever. And here's the counterintuitive thing about that lack of adjustability. For most applications, it was actually an advantage. A four-link suspension has multiple adjustment points, which means multiple opportunities to get the geometry wrong. And getting the geometry wrong on a four-link doesn't just mean slightly worse performance. It means dramatically worse performance. Racers in shops who didn't have deep experience with four-link geometry could spend months chasing a setup that actually put them further behind than stock leaf springs. Every adjustment point is also a failure point in terms of your knowledge and understanding. Ladder bars eliminated this problem completely. There was one geometry that worked well for most drag racing applications, and you either installed the bars at the right mounting locations or you didn't. The variables were drastically reduced, and reduced variables meant more consistent behavior. The construction itself was almost insultingly simple. Two pieces of steel tubing, typically 2 inches in diameter, sometimes 2.5. 4 rod ends to allow the pivoting action at each end of each bar. Steel plate brackets to mount the bars to the axle housing, usually just plate bent into a U-shape and welded onto the housing tube. Frame mounting points that could be as simple as tabs welded to the frame rails. That's the complete parts list. In 1975, quality rod ends and steel tubing would run you about $55 total. 35. If you sourced your materials economically. Any person with basic welding skills could build a complete set in an afternoon. Not a weekend. An afternoon. The installation guidelines were simple enough that they circulated through the racing community by word of mouth. Mount the front of the bars approximately 2 inches higher than the rear mounting point. Keep the bars as long as the car's geometry practically allows. Make sure they clear everything through the full range of suspension travel. Verify that nothing binds, nothing rubs, nothing restricts the suspension from moving freely. Then go to the track and run. No engineering degree. No complex geometry calculations. No sophisticated tools beyond the welder, a drill, and a tape measure. The barriers to entry were nearly zero. When this teenager first tested his creation, the results were immediate and dramatic. The rear tires didn't just grip better. They transformed. That sensation of launching a car that's previously been wheel spinning and hopping into a car that just bites and goes is something drivers describe with a kind of reverence. It's violent in the best possible way. The car goes from being something you're managing and coaxing to something that's just executing. Pure forward thrust, no drama. But the number that really told the story was the 60-foot time. Because 60-foot times don't lie and they don't get influenced by driver perception. For anyone less familiar with drag racing timing, here's why the 60-foot time matters so profoundly. It measures how long it takes to cover the first 60 feet from a standing start. That seems like a small piece of a quarter-mile run, but it tells you almost everything about a car's launch. Think of it like a rocket launch. The first moments of a rocket leaving the launch pad determine its trajectory for the entire flight. In drag racing, the first 60 feet determine the character of the entire run. A great 60-foot time means the car was planting power effectively from the very first instant. A poor 60-foot time means everything that happened after was playing catch-up. To put some concrete numbers around why this matters, a reasonably quick street car with decent traction might run 60-foot times in the 2.0 to 2.2 second range. A well-sorted performance street car might get into the 1.8s or 1.9s. Professional door slammer race cars with sophisticated 4-link suspensions and dedicated drag radials or slicks were running 1.3 to 1.4 second 60-foot times. These were cars with professional setups, professional tires, professional drivers, and thousands of dollars in suspension development. That was the benchmark for what serious performance looked like off the starting line. This teenager's ladder bar car, running on street tires, with $55 worth of welded steel tubing, was pulling 1.32 60-foot times. Not occasionally. Consistently. Run after run. Sit with that for a second. A Leaf spring car with stock-appearing suspension plus 2 parallel steel tubes was launching as hard as professional race cars with suspension setups costing 40 times as much. It's like showing up to a professional kitchen competition with a camp stove you bought at a gas station and producing a meal that beats the Michelin-starred chef. The established experts should not lose. But they did. Word traveled through the Tennessee racing community with the kind of speed that only exists when something genuinely unbelievable keeps proving itself to be true. Racers would show up at the track, see the ladder bars under this Chevelle, and some of them would laugh. Simple tubes. That's your trick? And then they'd watch the time slip come back at 1.32 60 foot. And the questions would start. What 4-link are you running? When they were told it wasn't a 4-link, the follow-up question was always the same. Then what is it? When the answer came back as just 2 bars welded to the axle housing and the frame, the response was predictable disbelief. Because the evidence was right there on the time slip, but it contradicted everything the racing community thought they understood about performance suspension. The professional racing establishment's initial reaction to ladder bars is almost charming in retrospect. They dismissed it. Of course they did. Chassis builders and suspension engineers had spent years developing the 4-link systems that were considered state-of-the-art. They'd made real innovations, real improvements over what came before. They understood anti-squat percentages and instant center calculations and geometry optimization. And this teenager with his welded tubes was contradicting their entire framework by simply doing it. The dismissal was partly defensive and partly genuine disbelief. How could something this simple compete with carefully engineered geometry? It went against the entire narrative that complexity equals performance. But here's what those experts were missing, and it's what makes the ladder bar story so instructive beyond just the racing world. A four-link suspension is theoretically superior to a ladder bar. Given perfect installation, perfect geometry, and a skilled tuner who genuinely understands the system, a four-link will edge out a ladder bar. The theory is sound. The engineering is real. But theory and practice are two very different things when you're talking about systems that require extensive expertise to tune correctly. A perfectly adjusted four-link beats a ladder bar. A poorly adjusted four-link, which describes the vast majority of four-links that amateur racers were actually running, loses to a ladder bar every single time. Ladder bars removed the tuner's skill from the equation. They provided one geometry that worked well for most applications, couldn't be adjusted incorrectly because they couldn't be adjusted at all, and delivered that geometry consistently regardless of who installed them or how much experience they had. You bolted them in, they worked, and they kept working the same way every time. For bracket racing especially, that consistency was worth more than the marginal theoretical improvement of a perfectly tuned four-link. In a sport where hundredths of a second separate winners from losers, consistent behavior is everything. Now let's get into the physics in a way that actually makes intuitive sense, because this is where it gets really interesting. When you accelerate hard in a rear-wheel drive car with leaf springs, you're not dealing with one force. You're dealing with several forces acting simultaneously, and the interaction between them is what makes predicting leaf spring behavior so difficult. There's torque trying to rotate the axle housing. There's weight transfer trying to compress the rear springs. There's the spring's natural resistance to deformation. And there's the geometric relationship between all the mounting points, which changes continuously as the suspension moves through its travel. Traditional leaf springs have what engineers call a floating instant center. As the springs compress and extend through their travel, the theoretical point around which they rotate is constantly moving. Not just moving a little, moving significantly. And because that point is moving, the behavior of the suspension under acceleration changes constantly too. A spring that's compressed from weight transfer behaves differently from a spring at ride height, which behaves differently from a spring that's extended. Each position creates different traction characteristics. This is why leaf spring cars were so inconsistent. The car that launched well on Monday's pass might not launch well on Wednesday's pass because track temperatures changed slightly and the springs compressed to a different point and the instant center moved. Ladder bars fixed the instant center. Not approximately. Mathematically. Those two parallel bars created a defined geometric relationship between the axle housing and the chassis that remained constant regardless of where the suspension was in its travel. The leaf springs were still present, still supporting the car's weight, still providing the vertical compliance that made the car drivable on the street. But they were completely relieved of any responsibility for managing rotational forces. They did their one job, the job they were designed for, while the ladder bars handled the acceleration forces with absolute precision and perfect consistency. The bar length mattered, but not in a complicated way. Longer bars meant less angular change as the suspension cycled through its range, which meant more consistent geometry across different ride heights and loading conditions. Shorter bars were necessary when packaging constraints made longer bars impractical. The typical installation used bars in the 32 to 36-inch range, which provided a good balance between geometric consistency and practical fitment under most production cars. The 2-inch height differential between front and rear mounting points was established through trial and error as the sweet spot that created the right instant center location for most drag racing applications. The brackets themselves were fabricated from 1/4-inch steel plate. Nothing exotic. The axle housing brackets were typically welded directly to the housing tubes, creating a connection that was absolutely rigid. The frame brackets could be welded on or bolted through the frame rails depending on the builder's preference and the specific application. Rod ends, also called heim joints, at each end of each bar provided two things: the pivoting action necessary for the suspension to move freely through its travel, and a degree of installation forgiveness that made the whole system easier to fit correctly in real-world garage conditions. The simplicity of the construction was genuinely part of the design's brilliance, because any component you don't include is a component that can't fail. Any adjustment point you eliminate is an adjustment that can't be made incorrectly. Any specialized knowledge you make unnecessary is a barrier you've removed for the next person who wants to use the design. The ladder bar, reduced to its essential elements, is almost impossible to get wrong if you follow the basic guidelines, and getting it right delivers performance that shocked an entire sport. The first drag strips in Tennessee to see ladder bars consistently perform started generating stories that spread across state lines faster than any advertisement could have. Racers talk. That's one of the foundational truths of motorsport culture. When something works, especially when something works unexpectedly, the story travels. By late 1975, racers in neighboring states were asking about the bars under those Chevelles. By 1976, fabricators in several markets were building ladder bar kits to meet demand. The idea had escaped the garage and entered the wider racing consciousness. Performance shops recognized the commercial opportunity almost immediately. Companies like Lakewood Industries, Competition Engineering, and Calvert Racing saw a clear market signal. Racers wanted this product, the demand was real and growing, and the design was simple enough that producing quality bolt-in kits for popular applications was straightforward. These production versions brought refinements that made sense for a manufactured product. Adjustable front mounting points that allowed some geometric tuning for different applications. Polyurethane bushings as an alternative to rod ends for street-driven cars, offering better durability and reduced maintenance in daily use conditions. Detailed installation instructions that made the product accessible to people who didn't have the original inventor's intuitive understanding of the geometry. But look, here's what's striking about every single production version that came to market. The fundamental design was unchanged from what that teenager built in his garage. Two parallel bars, pivoting at both ends, connecting the axle housing to the frame. Every refinement was in materials and convenience. None of the refinements changed the underlying mechanical principle because the underlying mechanical principle was already correct. You don't improve perfection in its fundamental form. You just make it easier to access. The professional racing establishment's acknowledgement of ladder bars, when it finally came, was reluctant in the way that any establishment's acknowledgement of a challenger tends to be. By the late 1970s, the time slips weren't lying, and time slips are the ultimate authority in drag racing. Leaf spring cars with ladder bars were running elapsed times that put them firmly in serious competition with purpose-built race cars. Not just in bracket racing, where consistency is the metric, but in index classes and even some heads-up formats where raw performance matters. The governing bodies of organized drag racing, NHRA and IHRA, updated their rulebooks to specifically address ladder bars. The fact that they needed to address them in the rulebook was itself an acknowledgement that ladder bars were legitimate competitive equipment. Some of the most impressive validation came from the stock and super stock classes, where rules require cars to closely mirror their factory configuration. In these classes, racers are working within tight constraints about what modifications are permissible, and the competition is intense because everyone is operating under similar restrictions. Ladder bars, which could be argued to leave the leaf spring architecture intact while simply adding a supplementary control system, became a crucial legal advantage in these classes. Cars that ran ladder bars in stock and super stock were consistently better off the line than cars that didn't, and the rulebook writers had to decide whether to ban them or accept them. They accepted them, which was the right call because the innovation was real. The Caltra bar, introduced in the early 1980s, deserves a moment of discussion here because it represents an interesting evolution of the ladder bar concept. Rather than two parallel bars, the Caltra system used a single bar with a spring-loaded preload mechanism. The operating principle was similar, controlling axle rotation while allowing vertical movement, but the execution was different. It split the difference between a pure ladder bar and a traction bar in a way that offered advantages in specific applications, particularly for cars that saw significant street use. While technically distinct from true ladder bars, the Caltra bar's commercial success confirmed something important. The market for affordable, effective axle control systems was large and enthusiastic, and there was room for design variations that served different needs within that market. The circle track racing community's adoption of ladder bar principles extended the technology's influence beyond straight-line racing. In circle track applications, the challenge isn't launching from a dead stop. It's controlling the rear axle under hard acceleration coming out of corners, where the combined forces of acceleration and cornering create complex load cases. Ladder bars and ladder bar-inspired designs helped racers manage these loads more predictably, translating to better corner exit speeds and more consistent lap times. The off-road community found value in ladder bars for controlling axle movement during aggressive climbing and acceleration in unpredictable terrain. Even towing applications benefited from the basic principle when dealing with the rotational forces created by heavy trailer load. The financial dimension of the ladder bar revolution is worth examining carefully because it illuminates something important about how innovation can reshape an entire industry's economic landscape. A typical 4-link conversion in 1975 cost approximately $3,000 in parts alone before labor. A ladder bar setup using quality components cost $55 to $80 total, including everything. That price difference isn't just significant for an individual racer. When you multiply it across the thousands of racers who chose ladder bars instead of 4-links in the late 1970s and throughout the 1980s, you're talking about an enormous amount of money that stayed in racers' pockets rather than going to chassis shops and suspension fabricators. Here's what most people don't realize about what that money meant for the sport. Money that stays in racers' pockets doesn't disappear from the motorsport economy. It gets redirected. Racers who saved $3,000 on suspension spent that money on engine development, on better tires, on more track time, on the entry fees to attend more events. The democratization of launch performance through affordable ladder bars actually expanded the overall racing economy by enabling more people to participate at a competitive level. When the barrier to entry drops, more people enter. More people entering means more events, more tracks, more aftermarket business, more of everything that makes a motorsport culture vibrant. The playing field effect was profound and immediate in bracket racing specifically. Bracket racing in the mid-1970s had a stratification problem that mirrored the broader social stratification of expensive hobbies. The racers with money for 4-link setups had a consistent performance advantage that was almost impossible to overcome without a similar investment. Ladder bars flattened that advantage overnight. Suddenly the guy with a bootstrap budget and a fabricated ladder bar setup was cutting 60-foot times that matched the guy with the full race setup. Now the competition was about driving skill and tuning knowledge and track preparation and all the things that should determine who wins a race, rather than who had more money to spend on suspension. This democratization wasn't just good for individual racers. It was good for the sport's identity. Drag racing has always carried the mythology of the common person competing against the establishment and winning on merit. Hot rodding culture is built on the idea that ingenuity and determination matter more than budget and pedigree. Ladder bars embodied that mythology perfectly. They were physical proof that the mythology was real, that a teenager with a welder could out-engineer the expensive alternative and produce results that shocked the professionals. That story resonated deeply with the culture, and it still does. Modern computer modeling and finite element analysis have done something interesting to the legacy of ladder bars. They've validated them. When engineers with sophisticated simulation tools analyze the geometry that teenagers stumbled upon through intuition and experimentation, they find that the basic mounting configuration he established is remarkably close to optimal for most drag racing applications. The front mounting point positioned roughly 2 inches above the rear mounting point, with bars in the 32 to 36-inch range, creates an instant center location that modern simulation identifies as effective for transferring weight to the rear tires during hard acceleration while maintaining straight-line stability. This is humbling in the best possible way. An 18-year-old kid with a tape measure and a welder figured out geometry that advanced engineering software confirms is nearly correct. He didn't have a computer. He didn't have a simulation tool. He didn't have an engineering degree or access to professional racing data. He had an intuitive understanding of how forces work, a willingness to try something nobody had tried before, and the specific focus that comes from being really tired of losing bracket races because your car wouldn't hook consistently. Necessity shaped the invention. Physics validated it decades later. The evolution of materials in ladder bar construction tells its own story about how the racing industry absorbed and refined the original concept. Early ladder bars were built from mild steel tubing because that was what was available and affordable. Modern performance versions use chromoly steel, which offers significantly higher strength-to-weight ratios. Some race-specific applications use aluminum components in non-critical areas to further reduce weight. High-end rod ends feature special coating treatments that dramatically extend service life under the contamination and abuse they experience in racing environments. Adjustable versions with multiple mounting positions allow racers to fine-tune the instant center location for specific applications, recovering some of the tunability advantage that 4-links have while maintaining the ladder bar's fundamental simplicity. But here's the crucial point that gets missed in discussions about modern refined ladder bars. All of these material and feature improvements are optimizations. They make good ladder bars into great ladder bars. They didn't make ladder bars possible. That happened with cheap mild steel tubing and basic rod ends in a Tennessee garage. Every fancy modern version is built on the same mechanical principle that the original designer identified. Control the rotation, free the vertical movement, fix the instant center. Everything else is refinement. The power levels that modern ladder bar setups handle would have been genuinely unimaginable in 1975. Cars producing over 2,000 horsepower successfully use ladder bar suspensions. Think about what 2,000 horsepower means in terms of rotational forces trying to wind up that rear axle. The forces are enormous, and modern ladder bars handle them with quality materials and proper construction. 7-second quarter-mile cars, vehicles covering the entire quarter-mile in 7 seconds from a standing start, have used ladder bar-based suspension successfully. The fundamental design scales. It worked at 200 horsepower in 1975, and it works at 2,000 horsepower today, because the physics don't care about the power level. They care about the geometry and the structural integrity of the component. The parade of would-be ladder bar replacements that the aftermarket produced over the decades is worth documenting, because it tells a story about how the racing market responds to established solutions. Every few years throughout the 1980s and 1990s, a company would introduce a new traction device that promised to finally supersede the ladder bar. Split monolith systems, torque arm designs, multi-link hybrids, sophisticated adjustable systems with multiple geometry positions. Each one came with engineering arguments for why it was superior. Some of them were genuinely superior in specific, narrow applications. None of them offered the combination of simplicity, broad effectiveness, and affordability that made ladder bars universally adopted. Most of them are no longer in production. Ladder bars are still on every drag strip in the world. There's an engineering philosophy lesson embedded in the ladder bar story that's worth making explicit, because it applies far beyond suspension design. Engineers talk about the concept of appropriate complexity. The right solution to a problem isn't necessarily the most sophisticated solution. It's the solution that addresses the specific problem with the minimum necessary complexity. Unnecessary complexity adds cost. It adds potential failure points. It adds knowledge requirements that limit who can successfully implement the solution. It adds adjustment variables that create new opportunities for error. The best engineering solution is the one that solves the problem completely while minimizing all of these unnecessary additions. Ladder bars are a textbook example of appropriate complexity. The problem was precisely defined. Axle rotation under hard acceleration causing inconsistent launches. The solution addressed that specific problem directly and completely. 2 bars that prevent rotation while allowing vertical movement. Nothing was added that didn't serve the specific problem. No adjustments that didn't need to be adjusted. No components that didn't have a defined function. The result was a solution so well matched to the problem that 50 years of engineering advancement haven't produced a fundamentally better answer for the specific application it was designed for. The patent situation around the original ladder bar design has an interesting effect on the industry that's worth considering. That Tennessee teenager never filed a patent on his design. Whether this was intentional or simply because filing a patent wasn't on an 18-year-old racer's radar, the result was that the fundamental ladder bar concept entered the public domain immediately. Any fabricator, any manufacturer, any individual could build and sell ladder bars without licensing fees or royalties. This absence of intellectual property barriers drove competition among manufacturers, which drove both innovation in refining the design and reduction in prices through market competition. By the time commercial ladder bar kits were widely available in the late 1970s, the pricing was accessible to virtually any serious racer. Compare this to a hypothetical world where the design had been patented and exclusively licensed. A single company controlling the intellectual property could have charged whatever the market would bear, potentially keeping ladder bars expensive enough that their democratizing effect on the sport would have been severely limited. The absence of a patent was, in this specific case, better for the sport and for the technology's adoption than the presence of one would have been. There's an irony in the fact that the teenager who could have made a fortune by filing a patent and licensing his design instead, by not filing, made a gift to an entire sport. The cultural impact of ladder bars within hot rodding and drag racing extends beyond the technical. They became a symbol. When you saw ladder bars under a car at the track, it communicated something specific about the car's owner. This person understands the physics. This person didn't just spend money. This person solved a problem. In a culture that genuinely respects ingenuity and street wisdom over credentials and spending power, that symbolic meaning mattered. Ladder bar cars had a specific reputation. They were serious. They were consistent. They were going to give you a real run regardless of what else was under the hood. The dual-purpose car concept that became enormously popular through the 1980s, vehicles that could drive to work during the week and genuinely compete at the track on weekends, was enabled in large part by ladder bars. Before ladder bars, running competitive elapsed times at the track basically required a dedicated race car because the suspension modifications necessary for competitive performance made the car unsuitable for street use. Ladder bars changed that equation. You could drive your car to the grocery store, drive it to the track on Saturday, run competitive times, and drive it home. The compromise wasn't perfect. It rarely is. But it was acceptable in a way that none of the previous solutions had been. This enabled an entire generation of racers who couldn't afford dedicated race cars to participate in the sport at a competitive level. The economics of drag racing participation shifted meaningfully when you didn't have to maintain both a race car and a street car, or choose between having a competitive car and having a car you could actually use. Ladder bars weren't the only technology that made dual-purpose performance cars possible in the 1980s, but they were a crucial enabling component. They solved the traction problem without sacrificing street usability, and that combination was genuinely transformative for how many people could participate in organized drag racing. Looking at the broader drag racing landscape today, nearly 50 years after that first ladder bar was fabricated in Tennessee, the technology's ubiquity is remarkable. Walk through the pits at any drag strip anywhere in the country on any given weekend. Look at the leaf spring cars. The overwhelming majority of them will have ladder bars. Not because the technology is new and exciting. Not because there's aggressive marketing pushing them. Because they work, they're affordable, and the racing community has had half a century to confirm that. A technology that earns that kind of sustained adoption across decades of continuous innovation in the surrounding sport isn't just a good product. It's a fundamental solution. The stories from racers who made the switch to ladder bars in the early years are remarkably consistent in their character. The reaction is almost always described the same way. The car just plants. The front description captures something real about what ladder bars do to the sensation of driving a car hard. Before ladder bars, launching a leaf spring car with serious power involved managing the car, feeling what the rear end was doing, making micro adjustments, trying to coax the tires into hooking rather than spinning. With ladder bars, the launch becomes almost mechanical. The car does the same thing every time because the suspension is doing the same thing every time. For a driver accustomed to fighting the car off the line, the first launch with ladder bars can feel almost anticlimactic. The work that used to happen simply doesn't happen anymore. And here's something that rarely gets discussed about ladder bars: their effect on driver development. When a car is inconsistent, drivers develop instincts and reactions that are responses to that inconsistency. They become very good at reading unpredictable launches and compensating for them. When you put that same driver in a consistent car, those compensating instincts can actually work against them initially. The consistency that ladder bars provide forces drivers to develop better fundamentals because there's nothing to manage off the line. The car is going to do exactly what it does. Your job is to drive everything that happens after that first 60 feet. The community of fabricators who built their businesses around ladder bars represents another economic legacy of the original invention. Shops that started as general fabrication or performance shops in the late 1970s built specific expertise around installing and configuring ladder bars. That expertise expanded naturally into related areas: rear end preparation, drive shaft work, chassis stiffening, complete car builds. The ladder bar created an entry point for a generation of fabricators who built careers around making leaf spring cars faster and more consistent. Many of the shops that are considered authorities on rear suspension preparation today trace their expertise back to early work with ladder bars. The instruction that flows from this story reaches beyond motorsport into broader questions about innovation and problem-solving that are relevant in almost any domain. The story of ladder bars asks you to consider where conventional wisdom comes from and whether the path from problem to solution always runs through complexity and expense. The professional racing establishment of the early 1970s wasn't wrong about four-link suspensions. They were genuinely better in theory. The mistake was the assumption that better in theory meant better for everyone in practice. An 18-year-old racer who couldn't afford the theoretically superior solution found a practically superior solution for the vast majority of applications. The lesson is that the best solution depends on who's using it, under what conditions, and with what resources. For anyone who has ever looked at an expensive, complicated solution to a problem they were facing and thought there must be a simpler way. The ladder bar story is validation that this instinct is worth following. Sometimes the simpler way doesn't exist. Sometimes the complexity is genuinely necessary. But sometimes, like with axle rotation control in drag racing, the simple way not only exists but actually outperforms the complex alternative when you account for real-world conditions of knowledge, resources, and consistency of implementation. Here's the thing about the teenager who built those first ladder bars. His name is obscure in most accounts of drag racing history. He didn't patent his invention. He didn't start a company. He didn't become famous. He just solved a problem that was bugging him and shared the solution with people around him, the way racers do. And yet, his invention has been used on probably millions of race cars over 50 years. It's in the pits at every major drag racing event. It's in the driveways of weekend racers across the country. It's in the engineering textbooks as an example of elegant mechanical problem solving. It changed the economic accessibility of competitive drag racing. It enabled a generation of dual-purpose performance cars. And it did all of this because one person refused to accept that expensive was the only path to fast. Every 1.32 60-foot time ever cut by a ladder bar car is a small tribute to that original insight. Every racer who bolted on a $50 solution instead of spending thousands on a 4-link conversion and ran competitive times anyway is living proof that the insight was correct. The physics were right, the geometry was right, and the accessibility was intentional, even if only intuitively so. You don't build something from the cheapest possible materials with the simplest possible construction unless, on some level, you want other people to be able to do what you're doing. Next time you're at a drag strip, take a moment before you look at the engines or the paint or the bodywork. Crouch down and look under the rear of the leaf spring cars in the pit. When you see those simple parallel bars running from the axle housing forward to the frame, remember that you're looking at one of the most consequential innovations in the history of the sport. Remember that those tubes, which look almost too simple to matter, changed who could afford to compete. Remember that an 18-year-old kid from Tennessee figured out in an afternoon what millions of dollars in professional racing development hadn't managed to solve affordably. And remember that sometimes the most lasting innovations aren't the ones that are the most complex or the most expensive. They're the ones that understand the problem precisely enough to solve it with exactly as much as the problem requires, and nothing more. Drop a comment below and tell us whether you've run ladder bars, whether you've got a garage innovation story of your own where the simple solution beat the expensive alternative. And if this kind of deep dive into the engineering stories that shaped motorsport history is what you're here for, make sure you're subscribed because we have more of these stories to tell. The best ones always involve someone refusing to accept that they couldn't afford to go fast.